Okay, so we're going to continue looking at our rotational equivalents of all of the linear translational quantities, and now we come to the idea of mass. And so the rotational equivalent of mass is called moment of inertia. Another name of it is called rotational inertia. And essentially we could define it as an object's tendency to want to rotate So want to stay in a state of rotation or want to stay in a state of rest. So in the past, we looked at the idea of mass being akin to inertia. And something that had a lot of mass had a lot of inertia. It was hard to get moving and it was hard to stop moving. The same thing can be said with moment of inertia. Something that has a really high moment of inertia, it's hard to get it moving and or get it rotating. And once it's rotating, it's hard to stop it from rotating. And moment of inertia depends on the distribution of mass. And essentially, the further away the mass is from the point of rotation, the higher the moment of inertia. So the further away the mass is from the point of rotation, the higher the moment of inertia is. And so I'm going to demonstrate that. I have a meter stick, and normally a meter stick center of mass is here at the 50 point, but I've added this 1 kilogram weight onto it. And so if I make my point of rotation right here, close to where this mass is, like the center of mass of this is clearly where the weight is now, it's really easy for me to rotate this. And so this has a really low moment of inertia. But if instead I decided to make my pivot point B over here on this end, it's really hard to rotate. It's really hard to get it moving because that mass is so far away from the pivot point. So this has a really high moment of inertia in that it's hard to get it moving, and once it's moving, it's hard for me to stop it from moving. Okay, I'm gonna put that down before I break my meter stick. There is a general equation for moment of inertia. So the symbol for it is I. And the general equation is that I is equal to the sum of the mass times r squared, to make sure. And it's looking at the distribution of mass. And so if you only have one object that's the distance of r away from the pivot, it's just mr squared. But if you have multiple objects distributed, you'd add them up. Okay? So m is clearly the mass, and r is the distance to the pivot, just like it's been for torque. Now, there are other specific objects, specific shapes, that have a very specific moment of inertia equation. And when we get back into class, I will give you a glue-in that has all those shapes defined and what the equations are. You are not expected to memorize them. They will either be something that are given to you or you'll be asked to solve for them. But your textbook also has that. So go ahead and save a place for a half-sheet glue-in that identifies common moment of inertias for specific objects. And then the video is now going to shift into looking at some examples of moment of inertia calculations. Okay, so we're going to go through a couple examples of moment of inertia. So this is a toy consisting of 2 balls, each 0.45 kilograms at the ends of a 0.46 meter long thin lightweight rod is shown. Find the moment of inertia of the toy about the center of the rod. So what that means is, like, this is the point of rotation. So this thing is either spinning like this or it's spinning around like this, but it's spinning from this point here. So if this thing in its entirety is 0.46 meters, then this distance for each of these, we'll say masses, is going to be half of that. So that's going to be 0.23. And we have two objects, and so the general equation for moment of inertia is, it's the sum of, general equation is that it is the sum of mr squared. So this is going to be 0.45 times 0.23 squared plus another 0.45 times 0.23 squared. And we would calculate that out. So you can pause the video, calculate that out, practice your calculating skills, see what you get. And you should get 0.0476. And I forgot to put what the units for moment of inertia were, but it's kilograms times meters squared. Okay? Okay, so let's try a second problem. Very similar. Each sphere has a mass of 0.1 kilograms. The distance between each one is 0.2. Find the moment of inertia if the rotation is about sphere A. So if it's about this sphere here, this distance from here to here is going to be 0.2, but then from point A to point C, that's going to be a distance of 0.4. So when we look to do our moment of inertia equation, that is going to be for sphere B, my mass is 0.1, and that distance is 0.2 quantity squared. But for C, that mass is 0.1, and that distance is 0.4 quantity squared. So you go ahead and calculate that out, and that is 0.02 kilogram meter squared. Now, if the point of rotation is around point B, that's going to be very similar to the problem we just did before, where I'm going to have essentially 2 times the moment of inertia. So 0.1 times my 0.2 quantity squared, where this is just my mr squared. And it's the same for each of them since they have the same mass and the same distance. So that in total is going to be 0.008 kilogram meters squared. And that kind of makes sense. Like if my point of rotation is here, I have a lot of mass way out here, I should have a higher moment of inertia. Okay, so now that you've looked at some examples of moment of inertia, we're going to revisit Newton's second law. So after we looked at the idea of mass, we looked at how forces affect a mass. And if moment of inertia is the rotational equivalent of mass, and torque is the rotational equivalent of a force, then we can rewrite Newton's second law. So if you recall, Newton's second law is this idea that the net force acting on an object, and we would look at the sum of the forces acting on the object, that's the dot, 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 and that was going to always equal ma. But we can have a rotational equivalent in that the net torque acting on an object is equal to the rotational equivalent of mass, which is inertia, a moment of inertia, times alpha. And so here is where we would sum up all the torques acting on an object. And first we looked at the idea of equilibrium where all those torques added up to 0, and now we're going to look at cases where the torques do not balance each other and a rotation does occur, and the amount of rotation that's going to occur is dependent on the moment of inertia. So the video is going to shift again and go through an example where you have a net torque that's causing an angular acceleration. Okay, so this is looking at when you have a net torque acting on an object and it's going to cause an acceleration, and you don't have it yet, but you will be getting a gluon that gives you some common moments of inertia for different objects. And I'm just going to tell you right now, for a solid cylinder, the equation for the moment of inertia for a solid cylinder is 1/2 mr squared, where m is the total mass and then r is the radius of the cylinder. So you've got this cylinder and you've got two forces acting on it, and you are told that it is pivoting about this point right here. So Newton's second law for torques is that net torque is equal to I alpha. So you have two torques. We'll call this one torque 1, this one torque 2. And if you kind of think about it, this 100 Newton one torque 1 is causing it to rotate in a counterclockwise fashion. Nope. And torque 2, this 80 newtons, is causing it to rotate in a clockwise fashion. So it would be that torque 1 minus torque 2 is equal to I alpha. And recall that our equation for torque is RF sine theta. So this would be R1 F1 sine theta 1 minus R2 F2 sine theta 2 is equal to I alpha, I in this case being 1/2 m r squared and alpha. So I do need to be careful. These are in centimeters, and I need to convert that to meters. So that's going to be, for R1, that's 0.12. Its force is 100. The angle between the R value and my force is 90, so that'll be sine of 90. Minus R2, that's going to be 0.08. Force 2 is 80. Again, the angle between my force, or my distance, and my force is 90. And that will equal 1/2. My mass is 50 kilograms. My R value, it's the radius of the entire thing, so that will be 0.12 times alpha. So pause the video if you need to pause the video, but go ahead and calculate out what that angular acceleration is. And you should get that it is 15.56 rads per second squared. Okay?